Okay, before we go any further with this, let's see how we would solve an equation of this nature, and then we'll do an example of an equation, non-homogeneous equation that can be solved using this method. Okay, so again, here's our equation, our basic equation for the variation of parameters. This is the equation we solve in order to get u1 prime and u2 prime. Now, I'll mention that having found u1 prime and u2 prime, we're going to have to integrate them, and sometimes that throws a hurdle into the process, but let's not worry about that just now. The question then is, how do we solve a matrix equation of this form? Now, among the prerequisites for this course, you should have encountered matrices. You should know about matrix multiplication, representing systems of equations as matrices, and so forth. And of course, if you've had a linear algebra course, which many of you will have had, this is rather straightforward for you. But some people are going to need a little bit of review or even a little bit of instruction on this. So let's take a minute and go over this. So in order to solve this equation, all we do is we basically multiply both sides by the inverse of this thing. If we had an equation ax equals b, we would multiply both sides by the inverse of a, the multiplicative inverse of a, in order to solve the equation. We're doing the same thing here. So we just multiply both sides by the multiplicative inverse of this matrix, which is going to give us the solution for u1 prime, u2 prime, and that's going to be the inverse matrix multiplied by 0g, by the vector we have over here. Now the question becomes, how do we invert a matrix? There are lots of possible answers. We can use adjoints if you happen to know what the adjoint means. We can use row reduction. We can reduce this matrix to an echelon form with elementary matrices and so forth. Many ways to do it. For a 2 by 2 matrix, for right now we're just going to deal with the 2 by 2 case, and for a 2 by 2 matrix I'm going to tell you all we do is we switch A and D. Well, let's back up to AB. Okay, if we've got a matrix A, B, C, D, just any old matrix of numbers or symbols or functions, whatever. If we've got a matrix A, B, C, D and we want to invert it, we reverse A and D and we change the signs of B and C. Now that's not a very sophisticated method. It doesn't translate over into higher dimensions because of course we can end up with matrices of 3 by 3, 4 by 4, etc. We can end up with much bigger matrices, and this method is not going to work for those bigger matrices. For bigger matrices, you're probably going to use row reduction or some semblance thereof in order to invert a matrix. Okay, in this case though, we just follow this simple rule, and the other thing is we got to multiply by the determinant of this matrix. Now certainly you would have seen determinants by now. You would have seen Cramer's rule in Algebra 2, I hope. And if not, then in a later course. The determinant is just this minus this, A times D minus B times C. So again, to invert a 2 by 2 matrix, we just switch A and D, we change the signs of C and B. We switch the main diagonal, we change the signs on the secondary diagonal, and multiply by the reciprocal of the determinant. Now that works. It works because why? Well, if we multiply A, B, C, D by D negative B negative C, A, what do we get? We get A, D, and B times minus C. So we get AD minus BC from multiplying the first row by the first column. Second row times second column gives us negative AB and then plus BA. And of course that gives us 0. And here we get second row times first column gives us Okay, CD minus DC in the second row times the second column gives us negative BC plus AB. Now, unfortunately, I've written all that kind of small, but AD minus BC is just this, and we have that here as well. We have negative BC plus AB, which is the same thing. So this, and this are the same thing. Therefore, when I take this product and divide by this determinant, I get 1 here and 1 here. And these two terms give us 0, so that gives us 0 and that gives us 0. And we see that we end up with the identity matrix. Now, I don't want to go too deep into this. If you don't understand what I just showed you, you should review matrix multiplication, inverse of a matrix, and a lot of things that you might be a little rusty on. I certainly hope you've seen those things by now, but the way the curriculum is written around some pretty poor standardized tests, I'm not sure everybody will have seen that. So make sure that you do research this topic if you don't understand what I've just shown you. The bottom line is that by inverting a matrix according to this rule, we can solve this equation, and the inverse of this matrix is just this. And all we're doing here, I've put this term over in front of the matrix. It's a multiplication by a constant. It doesn't matter which side it's on. If you're multiplying matrices, it does matter which side each matrix is on. So this is the rule. We're going to see how this works out. We're going to see how we use this rule in solving some differential equations. I'll also note that this only works if y1, y2 prime minus y2, y1 prime is not equal to 0, because, of course, if this was equal to 0, you'd have a division by 0. But this will be the case if y1 and y2 form a fundamental set.